everybody, welcome to Video Notes 2.3, Periodic Trends. We're going to be looking for some patterns today. So, as usual, make sure you can do these things after we're done here. Okay. So, and also, for your convenience, the book connection. So please read this stuff. Alright, there will be questions at the end. So, atomic size. What the heck is atomic size? Well, when we talk about atomic size, we're talking about the distance from the nucleus to the outermost electrons. So half the distance, if you have two atoms bonded together, half of the distance between their two nuclei is the radius. Okay, so atomic radius. What is the trend? So if you notice this, take a mental picture of this right now. So stare at it, take a mental picture, and if you notice, the atom size gets smaller going across that, and then the next period on the periodic table is smaller going across in the next period. It's a periodic trend. So why would atoms get smaller going across the periodic table? Okay, because the nucleus gets stronger, more positive, right? More positive. And so outer electrons get pulled in tighter, in closer. Okay. Atoms get bigger going down the table. Okay, so first of all, you see this picture, you see them getting bigger going down now. Okay, now, why would they get bigger going down? Well, whenever you go to a new period on the periodic table, you're putting outer electrons into a higher energy level. Where are higher energy levels? Further from the nucleus. Because electrons go into higher energy levels further from the nucleus. Okay, so the other thing, I think I might have put an extra letter in there, is that you have more protons as you go down the table. But when the electrons are going to a farther energy level, then you have all those core electrons, and then the outer electrons are kind of shielded from being pulled on by the nucleus. If you memorize this trend in atomic radius, atomic size, it'll help you know all the other trends. Okay, so I took out the transition metals and the intertransition metals. And now these are just groups 1A through 8A. And if you notice, you can see the trend again. Bigger atoms going down. Look at alkaline metals get bigger. Smaller atoms going across the period. And that same pattern repeats in the next period. Smaller going across. Okay. So now that we know atomic radius or atomic size, we're going to talk about a new property, electronegativity. The definition is the ability to attract electrons in a bond. So what is the trend? Fluorine is a what's up for electronegativity, and francium is, well, not. Okay, so where are they on the periodic table? We'll look in a second. So let's talk about why fluorine has the highest electronegativity of all elements. It's a small atom. It has a strong nucleus in its period because it has so many protons for its row. So it'll be easily able to attract bonded electrons. Okay. So the trend in electronegativity can be explained using the size of atoms and the number of protons. And size and more protons attract the outer electrons and another atom's outer electrons. Let's look at a periodic table. Okay, so what's under cesium? Francium. All right, and here's fluorine. It's the smallest atom that's not a noble gas. Right? It's the smallest atom that's not a noble gas on the right side of the periodic table. So it's got a strong nucleus first, strongest nucleus in its row besides neon. And so it's able to pull its own electrons in close and then pull another atom's electrons in. Give me your electrons, I'm electronegative. Francium, on the other hand, is the biggest element in its period, in its row, okay? And the biggest element in its period, so it's not going to be able to pull electrons towards itself. All right, so ionization energy, another definition. Okay, it's the amount of energy needed to remove an outer electron from an atom. So here's sodium. It has 11 protons, so it has 11 electrons. But if one of those electrons gets removed, 494 kilojoules per mole later, it's a sodium ion. Oh, look, it's a cation. Right? The amount of energy it takes to remove an electron is called ionization energy. So what's the trend? Group trend. So in a family, ionization energy decreases. Ionization, whoops, I don't want to put arrow down, right? Ionization energy gets smaller going down a family. Why could that happen? Well, it's easier to remove electrons from larger atoms since the outer electrons are farther from the nucleus and are shielded from the pull of the nucleus on the core electrons. So by the core electrons. So here's the nucleus. Here's all these inner core electrons, and then here's the outer electrons. So because the nucleus is blocked from pulling on that outer electron, the bigger the atoms in a group, the easier it is to remove an electron. See ya. Okay, so ionization energy decreases. It gets easier to remove electrons with bigger atoms. What's the periodic trend? What happens going across? Well, ionization energy increases across a period. What? Well, let's talk about why. Atoms are getting smaller going across a period, right? So these atoms over here are more able to pull their electrons in closer to them. So guess what? It's going to take more energy to remove them. Ionization energy is going to be higher to remove electrons. Okay. So now in any case, the valence electrons are the ones on the outermost parts of an atom. And so they're relatively easy to remove. But if you remove all the valence electrons from an atom and then try to remove a valence electron from the core electron set, they're going to be more difficult to remove. So we have this thing that we talked about called successive ionization energies. So you start with an atom. You take away one electron. Okay, maybe it was easy because it was a valence electron. You take away another electron. Okay, it was easy because maybe it was that has two valence electrons. But notice for magnesium, which we already know is in group 2A, forms a +2 charged ion. After its first two electrons, it has all of these core electrons that are pulled in closer to the nucleus. So you try to take an electron out of that 2p sublevel for magnesium that's trying to take a third electron. Look at the huge difference. From 1450 to 7,730. That's a huge jump compared to this, about doubled, right? 738, first electron takes 738 kilojoules of energy. Second electron took 1,450 kilojoules of energy. But the third electron, holy moly, that took like a heck of a lot more energy than the first and the second electron. Okay, so every time you try to take away an electron from an atom, it's going to cost you more energy each time. But look at this huge jump. Wow. Huge jump between this number and this number. So it looks like that third electron might have been a core electron. Okay, so you could explain what elements you have by looking at successive ionization energies. All right, explain the main way atoms differ, and you just said every trend. Okay, what do I mean? Okay, we know that atoms get bigger going down and smaller going across. Okay. And that's because nuclear pull on the outer electrons gets stronger as you go across because they're going in the same energy level. Nuclear pull gets weaker on the outer electrons as atoms get bigger because the energy levels are further from the nucleus. So nuclear attraction means more protons, means more attraction. But electron placement, the further the electrons away from the nucleus, the harder it is to attract them, especially if it's starting a new energy level. So nuclear pull, let's all pull together. And then long distance relationships are tough between a nucleus and electron on the outskirts. Okay, warning, warning, next slide contains snakes. So let's talk about ions. Ionic radius. So we know atoms get bigger going down and smaller going across. So then what would happen if an atom turns into an ion? So let's be over here with the metals. If this is a metal atom and it's going to turn into an ion, how? By losing electrons. Bye-bye, electron. Okay. So that means that when that electron's gone, the atom gets smaller. So cations are always smaller than their atoms. It's kind of like peeling away the layers of an onion. Right? Right, Shrek? Yeah. Okay. Electrons are leaving. So ion is smaller than original atom. Smaller than original atom. Original atom. All right. Anions get bigger than the original atoms. Why? Well, anions mean, and they happen over here on this side of the periodic table. All right. So you're adding an electron, and that electron is going to go and make the atom look bigger, and it has a charge. Okay. Adding electrons makes ion bigger than atom. Okay. Just like this snake is adding heads, and wow, it's getting bigger. I told you there were snakes. Okay. Octet rule. We learned about it already, but elements tend to gain, lose, or share electrons to have a full set of valence electrons. Refresher, valence electrons, highest energy level S&P electrons. So we got third energy level, S&P total. There's 6 valence electrons. So this element wants 8. It's going to put 1 electron right there, 1 electron right there. It'll be a -2 charge. Okay, 1 electron, 1 electron. So this is sulfur, -2 when it makes an ion. Okay. What about this atom? Well, highest energy level S&P electrons, 1 valence electron. What's easier, trying to get 7 more or just losing that 1? Well, sodium, loser, gives away its 1 outer electron. See you later, bye. And now it's an cation world. It's smaller than it originally was, and it's now got a full set of 8 valence electrons in its outer shell. Okay, valence electrons are the outermost electrons, and it's periodic. It goes 1, 2. 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8. Next period, 1, 2, 3 through 8. It's a repeating pattern. Yay! Okay, so metals and nonmetals react differently. We know that metals are losers to become positive ions, and nonmetals gain electrons to become negative ions. So, how are metals going to react differently? Well, big metals are going to be the most reactive because they're big, and so their outer electrons are going to be lost really quickly. So big metals, the best reactors for metals are big, unattractive losers. Big because their outer electrons, the bigger an atom is, outer electrons are farther from nucleus. So that means they're easier to lose. Nuclear pool. All right. Unattractive because outer electrons are in higher energy levels and energy levels farther from nucleus. And so they can't pull, the nucleus can't pull them in farther from nucleus. Okay. All right. Best non-metal reactor, fluorine. Fluorine is a small attractive stealer. Small because strong nuclear pool. Right. Attractive because smaller atom with strong nucleus can pull in other electrons. Okay, so reactivity is separated by that zigzag line, metals and non-metals. So metals get more reactive going down, where non-metals get more reactive going across. More reactive that way, more reactive that way. So it's opposite, what you would think. Yeah, more reactive. Oops. Yeah, okay. All right, so on the periodic table, the most reactive elements are big metals and small nonmetals. And these guys don't react. Full set of valence electrons. Okay. To review, there are groups and periods, and they each have a trend, so you have to know them. Atomic size is a major trend that can help you explain all the other ones. Metals are losers, but it's a positive thing. 8 is great. Quiz yourself, quiz me, quiz your family, quiz your lunch table. I told you there'd be questions, so go ahead and make sure you read these pages. All right, that's only 2. And then section 12.2 up to the end of page 344. And there's a picture to look at, figure 12.3, and then using that picture, answer these questions. Okay, so here's the objectives we talked about, and hopefully you learned a lot. Peace out.